And since then, since the middle of the pandemic, I live here in Bordeaux. But I was raised in Ukraine and spent the rest of my part in Ukraine. So while I was being raised there, my parents, they were very active observant of the political life there. Like it was a very young country. The state is essentially like 3 years younger than me, and there were like dozens of different political parties who were debating about how to build the country, and my parents were watching all of that. A huge amount of time of TV prime time was taken by the political talk shows. Like the one on this screenshot. The idea was that they were inviting some politicians in order to discuss the matters, and they were giving some speeches. They were discussing, debating, and there were also an audience. You can see that this like central place is surrounded also with some people. Those are ordinary people who were invited to the studio, and they could give a round of applause. They could ask questions, but also what they were doing was continuously giving feedback to those politicians debating using a special device. If you zoom in on that picture, you'll actually recognize that those people, they are next to a special device that gives them an opportunity to vote and indicate whether they agree or disagree what is currently being spoken about. And it was very interesting to observe how those participants of the actual debates were reacting to those stats. They had like real life time stats about whether the audience is supporting that or not. It was very entertaining on the TV. And since that childhood, I got a dream. I wanted to participate I wanted to give a speech and have a real and real-time feedback from my audience. So today, I invite you to participate in making my dream true. Let's scan this QR code, use your mobile device as like that device. I will do the same to test that it is actually working. What you will see is a very simple web page that displays you 2 buttons. The question there might be slightly different every time, but the main idea is that it is asking you whether you still agree with what I'm talking about, if you follow or you disagree, and that doesn't make any sense. The question will be changing a little bit, so feel free to push the buttons, and we'll try to see what is your reaction during this talk. As you might have guessed, I will be trying to visualize your data sometimes, and I will try to do my best not to look at this graph too often, because maybe I will get demotivated and I need to finish my talk. But we'll see how it can help. But what this talk is really about is that I want you to think with me together about the design of this application and how we deploy and expose and make it actually usable. Thanks for that, testing. And how we can make this application usable in the context of giving this talk. So let's start from a simple design exercise and reviewing our use cases, right? Because if you imagine building a system, a small system like that, we need to understand what we need to put together. And my immediate thoughts were, okay, if I want to do something like that, I will make some server that participants, meaning you, will be able to communicate, interact with, and submit your opinion about. So we have the first type of transaction here. It is participants voting, submitting their data, their opinion to the server that has to keep the data. Next, we have a presenter, meaning me, who will be trying to also give some context to this data. Because if you just have the votes, and we imagine that we have timestamps for those votes, right? We can graph and have a graph like how people in time were reacting, but maybe to analyze the speech and the presentation, that will not be very helpful, or like it will be quite difficult to associate when people were agreeing with what matters with what sections of my presentation. So as I'm moving on with my slides, I will be continuously updating the context, and I will be submitting that, okay, at this moment of time, we are at this particular section of my presentation, so that then we can fuse the data from you and from me, and have some statistics per topic in my presentation. So that's what we'll be calling the annotation use case. And finally, me as a presenter, I want to visualize this data, right? So I need to fetch that aggregated data and present to you, like on that graph, and get some meaning from there. So if we summarize, we get a system where we see three types of interactions or operations. All of those three types of operations could be described as request response to the server, right? For both voting, annotating, fetching the data, it's all about sending a request and getting the response. And we have three types of those interactions: voting, annotating, and fetching. So this part, I have to apologize and say that here I probably end the most understandable part of my presentation, because what I'm going to do next is to show you a bunch of different pieces of code and try to explain why I'm showing those pieces of code and why I'm doing that in code, with code, and not in some other way. Maybe at the beginning something will look a bit weird. I hope that will resolve your confusion in the end. So let me start from trying. So we saw those three use cases, and what I want to do next is to start putting those use cases in code, like describing those use cases and putting some metadata that describes how I can define the use cases so that I can work with them and derive something from them. So speaking about each of those use cases, which are the request-response kind of interaction with the server, I can say that, for example, for voting, I can imagine that I will give you an opportunity to submit a new vote every 5 seconds, right? So I can say that the submission rate there will be every 5 seconds we get a new vote. And I need also to imagine how many users I will be dealing with, right? How many people will be submitting that. If you think about Bordeaux conference, and if I was lucky enough to get an amphitheater A here, I could have 1,000 people. And in general, we have here 1,000 people at the conference. So we can assume that maximum number of concurrent users is 1,000. So we put it into something like a JSON document, right? Next, what I'm going to do is to represent the same data with a slightly different language. It's not JSON anymore. It's a language that is called Q. It stands for configure, unify, and execute. It's a language that was created for simplifying the task of writing different configurations. I will be using examples in this language for a particular purpose. I will talk about it in a second. But in general, it is a JSON superset. So any valid JSON is a valid queue. But here we can also remove some quotes and some commas and get the same data representation here. But what Q is about is not only about removing those quotes, that would be YAML, but Q is more about mixing the data with their schemas and defining also some constraints on the data that you can put together. So what I'm going to do is to say that, okay, when I describe my use cases here, I will make some rules about how I can describe them. So we say that my use cases definition is a dictionary that has a use case name, and then it is described with 2 fields, submit period that has to be a string, and number of concurrent users that has to be a number between 0 and 1 million. If I put anything more than 1 million, that's probably a mistake, because I don't imagine how this application can be used by more than 1 million concurrent users. That's definitely a mistake. So what Q allows me now to do is to execute something like a qvat command on my data with those constraints. And if I put something like 2 million there, it will say, hey, Roman, you're wrong. This data doesn't satisfy the constraints that you put in there. We can define even more constraints. We can say that that the submit period has to be a valid duration string, meaning that it has to look like something like F5S, meaning 5 seconds, or 5M, 5 minutes. So it has to be parsable duration string. If it is not, that's a mistake. And even more, we can say that I cannot add anything else to my use case definition. Like if I add something like the third field, like full bar, that will mean that it's also a mistake. I'm violating my schema of the data. So putting all of that together, we can finally describe our use cases. So for voting, that's what we saw already. For annotating, let's imagine that I get to agreement with some other speakers here at the conference. They will be also using my solution, so I will not be the only one, but we'll have 10 speakers annotating the data. It should not be every second, right? Because I spend some time on my slides. I switch between topic spending some time. So let's assume 2 minutes. And for fetching, that should be probably more frequent because I want to almost in real time show you the data. So every 5 seconds you'll be getting that aggregated data, and the number of concurrent users is equal to the number of presenters. So I'm referring to the same number of users that I have for annotation use case. Right, so let's try to check. Okay, still some people are still following. I didn't lose you completely. So now let's try to get some usefulness from all this work that we have done. We put some data describing our use cases for what reason. In my opinion, we did that for now having a formal way to calculate something like a call per second rate. Because if I deal with this server, right, the first thing that I want to understand is, okay, how frequently those like request response interaction will be happening, and that will give me some idea about the load that my server will be coping with. So from this model that we already put together, we can get the calculation per use case because we know the number of concurrent users or assumed number of concurrent users, the expected number. We can divide that by that submission rate, and we'll have the call per second rate for that use case for our application. So if you try to evaluate that with Q, it will give us that, okay, for voting, we'll have something like 200 calls per second, for annotating less than 1 call per second, for fetching data 2 calls per second. Now, my next question was that, okay, in fact, I'm all doing that in order to understand that okay, I have this idea of the application. I want to understand how I will be deploying it. Right? So call per second gives me an idea of how much load I will be coping with. But can I also assess the storage that I need? Because people will be submitting the votes. I need to understand what kind of storage I need in order to sustain that the data. For that, I typically, like my main language that I code with is Go. And to begin with assessing the storage that I need, I would start from defining the data structures that I need in order to represent the data, right? So I would start from taking the vote use case and thinking what is the structure that I need for voting. So that would be some structure that has the talk name, because I want to understand what vote this is related to. It would be a timestamp, for example, an ISO string representing the timestamp. I need a voter ID, something anonymous, but still something that would allow me to distinguish people, because what I want to do is to visualize the number of people who agree or disagree. So I need a unique thing, and when you submit the votes, they should be having the same ID in all the votes coming from the same person. Finally, we need the opinion, right? And in our case, it could be maybe a Boolean, but let's think that we'll extend it to other use cases and make it a number between 1 and 10, 1 meaning I completely disagree and 10 I completely agree. So that's the data structure for voting. Similarly, we would need a data structure for labels, meaning that we have a timestamp, we have a label, meaning what is Roman talking about right now, and of course the talk name. And now when I have these data structures, that can give me some understanding of how much space they will be taken. And in order to do the calculations, what I can do, particularly with Q, is that I can import those data structures in my Q definitions that will give me the schemas of those data structures. And with that, I can start adding some examples of the records for all the use cases that I deal with. So for example, for annotating, I can describe an example or give an example of a record that will be storing for every label that will be submitted by a speaker. I will do that by generating a talk name that will be 800 symbols, give an example of a timestamp that will be storing there, and a name that will be 50 symbols long. Why I'm doing that is because this sample record can now be transformed into a particular serialized sequence of bytes, the length of which will give me the actual storage that I need to keep the record. And one of the simplest way to store it would be to serialize it in JSON, take the length of the obtained JSON document for that record, and that would give me the number of bytes that I need to keep in my storage to keep the data. It's of course not a very optimal way to store the data, but it gives me some margin of how much space I need. And what is nice is that if I keep updating my structures and adding more data, it will grow together with those updates, because this is linked to the data structure that I have in my actual application. So as a result, now, in my use case definition, I can add the calculation of the memory that I need in order to sustain that use case. Because we know, again, the number of concurrent users, we know the submission rate, we know the size of a single record. We can calculate how much memory we will need for our conference duration, like for example, during 5 or 8 hours. Finally, we can build a summary of that, summing up all the calls per second for each use case, summing up the memory usage for each use case, and get something that looks like a requirement for my system. So it means that my server that was on those diagrams will need to deal with the 202 calls per second, and it will need 900 megabytes in order to store the data for an event. Which immediately triggers the thought that, okay, maybe that's not a lot of memory. Maybe I can keep that memory, all the data in RAM, and I don't need a very sophisticated architecture for this app. So at this point, you probably start questioning why I'm showing all of this code, especially let's verify that. No, you keep submitting that you agree. I'm surprised. But what I would do in your place was saying that, okay, Roman, what you are currently doing is an equivalence of a classical system design exercise. I don't know why you're doing that. Maybe you're practicing for the interviews. That's what people typically ask there. But it's easier to do it on paper, and we call it typically the back-on-envelope calculations when we have a task of understanding, okay, if you want to put this system in place, how much resources we'll need. And to convince you that it makes sense to do it in code, not on this piece of paper, I think that I can do that only by showing you more code. So stay with me and bear with me. Let's imagine that we deploy this application to a Kubernetes cluster. And when we work with the Kubernetes cluster and describe Kubernetes deployment, we typically have an ability to specify the resources limits or our resources expectations for deployment. So now if we write our deployment definition, we actually have a direct way to say that it's not a magic number of 900 megabytes of memory that we want there, but it is something that is derived from the usage model of our system that we put together. So this we get a formal way of replacing some magic numbers in our configuration with something that comes from maybe a bit more meaningful numbers that we can understand and reason about, that we dealt with at the very beginning. Or another use case, let's say that I want to put an application firewall in front of my server, because I hope that you will not be spending time abusing my application. You will be quite interested in listening to me, but if you decide to abuse it, I probably want something to protect it. And when I define that Terraform definition, saying that I want to configure the AWS web application firewall there, and I want to configure the maximum rate of requests per IP address, I can say that it cannot be lower than the calculated call per second, right? Because otherwise I will be blocking the legitimate users. And this kind of constraint will help me to validate that my firewall configuration is not completely broken. So now let's ask a question. Okay, like, what about this particular server that you're currently using? How is it deployed? And with this question, I want you to bring you remember that number of 900 megabytes, and that was what pushed me to think, okay, can I get away with that with a single server? So we started exploring what we have on AWS, and on AWS we can do something like an API call or a CLI command that describes all the possible instance types that are available on their EC2 service. And that description that is returned there is actually array of data. It can be a JSON document that we can import in queue, and as a result get a list of all the possible instance types with their characteristics. It will actually tell you how many virtual CPUs it has, and what is nice, it will also have the number of megabytes that will be available on those machines. So it means that now I have this data about their AWS offerings, and I have my usage model, so I can build a filter for those instance types from my usage model and find the instance type that satisfies a constraint, saying that, okay, this instance type must have the amount of megabytes that is higher than my requirement from the usage model, but probably lower than the doubled amount of that amount. That gives me a list of 8 instance types. Among them I see one that is called T3 micro. It triggers some memory that probably it is something legible for the free tier. So I modify my filter and say that, okay, I also want to check whether those instance types that are legible for free tier, in a programmatic way, in a formal way, I get a proof that I can get away with a free server on EC2 in order to get your opinion on what I'm talking about. So in the end, my deployment looks like a Terraform definition that has an EC2 server of an instance type that is derived from the memory requirement that I had in my usage model, and with an image that satisfies the requirements of that instance type, and that's how the server is deployed. When I was thinking about that, so I was getting excited. Okay, I can get the server for free, and I can get all your opinions about what I'm talking about. But it will be a server with a single CPU, right? That micro instance, it has just a single CPU. And I will need to deal with the 200 calls per second. I was thinking, okay, is it a lot for the CPU or is it not? Of course, it depends on how quick is my code processing that request, generating the response. But then I started thinking, okay, what are other examples of applications that are using a single CPU, like single-threaded? And my next answer was that those are the UI applications. In UI applications, you have typically a target that you need to generate the frames at 60 frames per second rate. It gives you around 16 milliseconds to generate a frame. And they're pretty good. They work on many machines, and they can generate the frames and have smooth animations. So it told me, okay, I have one CPU on that server. Can I get to 60 calls per second so that I'm comfortable processing all the requests? If I put a constraint to my CPS that has to be not more than 60 calls per second, I will violate it, because my calculations show that it is actually 200. But we see that the voting use case contributes mainly to that call per second. So I play a little bit with that submit rate and a little bit enlarge it. I will get the number of 20 seconds and will satisfy my constraint of 60 calls per second for my server. So that's why when you now again press on the button that you agree with me, you will see that you can submit again in 20 seconds. So that's how the configuration of that web application is derived from the usage model as well. So getting back to the question why I'm showing these slides with the code, I'm saying that the reason number one why I believe that it is useful to put into the code is because it can help us to maintain and validate our deployment code. Because I think that we won't find people who will disagree with the fact that keeping our infrastructure in code or our infrastructure definitions in code is very helpful and helps us to maintain the live systems. But when we derive the configuration for those definitions, it might be better to get those magical numbers from something meaningful. But there is more to that, and I think that if you try to now step back about what we were doing, we can formulate actually a process that I nowadays call usage model-driven development. So we begin with defining our usage model, like understanding how our system will be used. From that usage model, it helps us to shape our deployment code, the configuration of our deployment, understand what the deployment should look like and how it should be configured. Then when we have a deployment, we typically try to observe it and understand whether the system functions okay or not. That is done by exposing some metrics. The usage model can give us a good answer to what those metrics should be, because in the end, those should be the metrics that we want to compare to our usage model and refine whether our model, our expectations, should match the real-world scenarios. And with that approach, we get into the loop where we start from our expectations, we get to the deployed system, and we can verify whether our expectations keep matching the real-world scenario. To illustrate, and in my mind, this concept is slightly similar to test-driven development, because in test-driven development, you also start from your expectations expressed in a test. Then you can continue with making the implementation, which is shaped with your tests. And then you see whether your implementation satisfies those expectations, and you're in that loop. It's a very different time loop. Like the iteration is very different, of course, because we are talking about the deployments and maintaining the system. So it may be a loop of weeks, maybe days, depends on how you work with the system, but still a well-defined loop of how you can not lose track of what you expect from the system and what is actually happening. So to illustrate, and what you will find in the code of the server was that I talked a lot about the memory usage. So once I have a deployed server and I deployed it to AWS, so I can use their CloudWatch mechanism in order to get the metrics reported by the server and check the actual memory usage. Right? If I invoke that command of asking AWS, hey, give me the data points for that memory usage metric, it will give me again an array of data, which I can import into my definitions and define a constraint for that data, because this actual data should satisfy my expectations. So I know it shows me that the actual usage is 19%. From my deployment, I know what is the memory, maximum available memory is available on my server. I know what should be the memory taken by my application from the usage model, so I can calculate the expected percentage of the memory used and verify whether it's satisfied, this constraint is satisfied. After some tests, I was testing these applications, trying to submit some data. I discovered that it is actually not true, because I didn't take into account the fact that on my machine, on my server, I also run the CloudWatch agent that consumes a little bit of memory, and my expectations about this system were a little bit wrong. So I had to refine the model and iterate it on it, and that's an example of that loop that I was presenting. So the reason number 2 for doing your system design in code is that you get a programmatic and a formal way of confirming that your system design matches the real world. Because otherwise it is quite easy to lose track and be lost in all the metrics and all the use cases that the system deals with. So if you think now about what I was trying to talk about, so I was talking about the idea of usage model-driven development. I think that Q might help in there. It is a young language. But be aware it is really young. It is quite hard to use in production. There are quite a few different bugs in how their evaluator works. But it's not about Q, right? Because this approach of putting your expectations about the system in code can be implemented in very different ways. If you deal with the cloud development kits, where you express a deployment in a language that you use on a day-to-day basis, like in TypeScript, in Go, in C#, it should also be perfect, because in that general purpose language you can also express your expectations and you can define the rules and constraints of what you should see from the real-life system. So long as you keep doing the exercise and keep thinking about this usage model, I'm happy. If you start being convincing that it might be useful not to keep it on paper but move to the code, I'm even more happy. And you can check an example of this poll server that you were using on my GitHub repo. With that, I really thank you for the attention. And let's check what are our final results after getting the conclusions. Okay, and we can, for those where I lost you in some sections, we can discuss in the questions and answer part of our conversation. Thanks a lot. There was a lot of disagreement about the EC2 deployment. Who wants to ask a question about that? N'hésitez pas à poser la question en français aussi. Je pense que je peux parler. Peut-être que je vais répondre en anglais, mais je peux comprendre aussi.
Je ne parle pas français. I can just speak in English. My question is, you show this example, it's all kind of simple demo, small code. Are you using something like this in a production environment, in something bigger, something more you can talk about?
Yeah, sure. So yes, it's absolutely true. My example is more like for pedagogical purposes, right? It doesn't reflect the real systems that we deal with. However, I think that it pushes you to think like it is a useful thing, right? So we can deliver useful things with some small pieces. But indeed, if you talk about the real use cases that I'm dealing with, this idea of usage model-driven development was derived from the practices that we have in my team. I work at Ubisoft. We deal with game streaming solutions. We launch the games on one machine, we stream them to another, and let people play those games. So we deal a lot with the questions of infrastructure and how the applications interact with that infra. And from the practices that we have there, this idea was derived. And I cannot tell you that all our infrastructure is derived specifically from the usage from the usage model, but we have it in a few places, and especially like we have an ongoing topic, quite a big challenge that we approach specifically with this framework in mind.
Thank you. How often do you reevaluate the initial model? Is it automatic to reevaluate the resources and push new resources, or do you do it manually?
So in my example, you will not see any CI pipeline on my repo. You will just have a bunch of scripts that allow you to deploy the server and validate it. Like there is a script that gets the memory metrics and verifies them according to the usage model constraints. So I would say that's up to you. But indeed, I can imagine the automatic process, but I don't have examples where it is really like fully automated. In my opinion, what is important is to have this kind of mindset, thinking about how we deal with the systems. If we find that some pieces are not very hard to automate, that's definitely worth doing at some point.
Thank you.
Merci beaucoup. Bonne journée.